So on page 85, we're looking at the natural log function. So we need to come up with a Taylor polynomial centered at a equals 1. All right. It would make sense not to use a equals 0 because natural log of 0 doesn't exist. All right. So we would want to focus on reasonable values, and what's more reasonable than the number 1 for a natural log. Natural log of 1 is equal to 0. All right. So that's a nice value to work with. All right. So let's get our derivatives involved here. N equals 6, which means I need the sixth derivative. So f of x, ln of x, f prime of x is 1 over x, but I'm going to write that as x to the negative first. F double prime, negative x to the negative second, to the third, 2x to the negative third, fourth derivative, negative 6x to the negative fourth, fifth derivative, and that's 24x to the negative fifth, and sixth derivative, that's going to be 120, negative 120, x to the negative sixth. All right. So we have those derivatives in play here, or in place. Now we want to evaluate it from when x is equal to a, which is equal to 1. So all of these values evaluated when x is equal to 1. Trying to stave off writer's cramp here. All right, natural log of 1 is 0. 1 over 1 is 1. Negative 1 over 1 squared is negative 1. 2 over 1 cubed is 2. Negative 6 over x to the fourth, so negative 6 over 1 to the fourth is negative 6. 24 over 1 to the fifth, 24. And so negative 120. All right, so that number 1 was beautiful in more ways than one. All right. So building our Taylor polynomial, remember it's not centered around 0 anymore. So p sub 6, poor quality 6, of x, we're going to start off with, again, I mean, if you just kind of look at the rule here, you start off with the original function evaluated at whatever the center value is, in this case 1, then the first derivative as a multiplier of x minus whatever the a value is, and then we, bearing in mind that those denominators are always factorial, starting with 0 factorial and increasing from there. All right, so we're looking at 0 over, well, I could say over 0 factorial times x minus 1 to the 0th power, but I think you'll forgive me if I just write the 0. All right, plus 1 over 1 factorial times x minus 1 to the first, plus negative 1 over 2 factorial x minus 1 to the second, plus 2 over 3 factorial x minus 1 to the third power, plus negative 6 over 4 factorial x minus 1 to the fourth, plus 24 over 5 factorial x minus 1 to the fifth, and then finally plus a negative 1, 20 over 6 factorial x minus 1 to the sixth. All right, so that's a lot, but in theory this should be a pretty good approximation of this natural log function. Now we can clean it up just a smidge. There's not really much we can do, but we can say if we wanted to, we can get rid of the 0. We could make the first term x minus 1, first quote-unquote term, the binomial, negative 1/2, x minus 1 squared, and so on. But then after a while, he starts questioning what the need is for that. All right, there are some things that cancel out nicely, not completely, but in a nicer way. Like, for example, 6 factorial is 720, but it's really 120 multiplied by 6. All right, so it'd be negative 1/6. All right. If you really think about it, in each case, it actually kind of cleans up in a way that might not be as expected if you start getting into rote computations, because if you really kind of consider what each coefficient is in terms of a factorial, you can kind of save yourself some time and energy. All right, so that 6, for example, is the same as 3 factorial. That 4, for example, is 4 times 3 factorial. That 24 is 4 factorial. That 5 is 5 times 4 factorial. All right, so there is that relationship that keeps popping up. This is 5 factorial. This is 6 times 5 factorial. All right, so like I said, you can save yourself some time and energy if you come up with those little nifty shortcuts. All right, but we did get the job done. We did figure out what we needed to figure out, so we're in pretty good shape. If you want to simplify or not simplify, that's up to you. I'm just going to clean it up a little bit, but just understand on a test, if I ask you to come up with a polynomial, I just need the polynomial. All right, if you don't see the directions and simplify, then do not simplify. You're asking for trouble. All right, in the sense that you might make a mistake and you lose credit for something you never had to do to begin with, and that stinks. It more than kind of stinks. It absolutely stinks. All right, so x minus 1 cubed minus 1/4 x minus 1 to the 4th plus 1/5 x minus 1 to the 5th. Let me just smidge it over a little bit. Minus 1/6 x minus 1 to the 6th. All right. So the Taylor polynomial of degree 4 for x, e to the x minus 5. All right. So that's a fun one. Centered at x equals 5. Now you see the convenience of that comes into play when you look at the x value being a convenient x value for the purpose of simplifying the expression substantially. All right, so look for that. If you have a choice on how to center your polynomial, that's something that you should be looking for. What's the nice convenient value for the transcendental function you're working with? All right, so as far as derivatives are concerned, though, this is nice because f of x is going to have a derivative of e to the x minus 5. The derivative of the exponent is 1, so that's not going to change. So every derivative is going to be e to the x minus 5. So at 5, it's 1 for the original function, and every subsequent derivative, the result is going to be 1. All right. So when I come up with my polynomial for degree n equals 4, I just need to go out until I get to the 4th derivative. So my first derivative, or my original function evaluated at 5 is 1, plus my first derivative evaluated at 5 is 1 over 1 factorial times x minus 5 to the first power, plus 1 over 2 factorial x minus 5 to the second power, plus 1 over 3 factorial x minus 5 to the third power, plus, now we're out, so 0th, 1st, 2nd, 3rd, one more, and we'll have our fourth derivative, 1 over 4 factorial x minus 5 to the 4th power. All right. In terms of housekeeping, there isn't really much to do, because even if I evaluate or simplify my factorial, it's not like it's going to simplify to the point where I can cancel anything. So this is pretty much how we would leave it. All right. Now, for the last example here, it says suppose that g is a function which has continuous derivatives, and that g of 2 is equal to 3, g prime of 2 is equal to negative 4, double prime of 2 is equal to 7, so on. It's saying go out to degree 3 centered at 2. It's given us all the hard stuff. We got everything we need here. So if I need a polynomial of degree 3 centered at 2, it's going to be 3 plus a negative 4 over 1 factorial x minus 2 to the first, plus 7 over 2 factorial, that's my second derivative, x minus 2 to the second power, plus negative 5 over 3 factorial times x minus 2 to the third power. And a problem like this would only get more challenging, or I would say prohibitively challenging, if they gave you this information and then they said write the Taylor polynomial of degree 20 or even degree 7, where you had to figure out what the trend was in the coefficients. But that's not what they asked for, so we're in pretty good shape here. And so that's all there is to it, because like I said, even if I did simplify, it's not going to simplify in such a way to enhance anything. So that's where we leave it.